We've already calculated eigenvalues and eigenvectors for 2x2 matrices before, but let's ramp it up a notch and do it for 3x3 matrices. Awesome! However, therefore I am obliged to point out that if this video is your first ever experience of calculating eigenvalues and eigenvectors for a matrix, then just don't, because you really should watch the video on 2x2 eigenvalues and eigenvectors first, partly for the sake of your sanity because it's much easier to start with 2x2 matrices, but also because I'm going to skip over some of the explanation in this video because I'm assuming you've already seen it in that other previous video. So how do we find the eigenvalues of a 3x3 matrix? The answer to that is exactly the same as we did before. The eigenvalues lambda are the solutions to this equation. And then once you've found the eigenvalues, you can find the eigenvectors by first of all realizing, because we're dealing with a 3x3 matrix, the vectors are going to be 3D vectors, but these vectors are just the solutions to this equation, where you have an eigenvector that's paired with the particular eigenvalue you're using to find it. Because this is so similar to what we did when finding 2D eigenvectors, you might be wondering why I even bothered making this video if it's contributing nothing new. Well, actually it will, but you'll only start to see that when we start actually trying to find the eigenvectors, so bear with me when we get to that point. So let's launch into an example. We need to find the eigenvalues and the eigenvectors of this 3x3 matrix. Now, if you're lucky, if you're trying to do this in a question, most of the time they should be kind and include at least one, maybe even two or more zeros in your matrix, which will speed up the process of finding the determinant, which is of course part of finding eigenvalues. I haven't done that here because apparently I enjoy just multiplying out brackets all day, but there you go. It is worth mentioning, therefore, if you're studying this content at a university where only minimal calculator use is allowed in exams, it's probably unlikely you'll even be asked to do the eigenvalues and eigenvectors of a 3x3 matrix just because of the heavy amount of calculation that's required. But as we're at A level where we are allowed to use a calculator, I will be making use of that as I go. So let's start off by calculating the eigenvalues. So to do that, we basically need to solve this as an equation. The determinant of this 3x3 matrix, which is basically the same as the one given to us in the question, but with every element in the main diagonal having lambda subtracted from it. All the other elements stay the same, and then this determinant has got to be set equal to 0. Now, the advantage of watching this as a video rather than an in-person demonstration is that as I'm speaking right now, I'm having to write all these lines of working out, and it's already taking forever, and I'm already regretting doing this example, but you will get to see me writing all these lines of working out in double speed, maybe even more, because I've already decided in editing I'm going to speed up the video of me writing this stuff out. So, lucky you, and I will see you in a few moments, or speak to you in a few moments, once all this writing out of algebra is done. And so, after all of that, we got this cubic, and ultimately this is what I meant about calculator use, because at this stage, if you're able to do this matrix stuff that we're looking at the moment, then ultimately I'm assuming you already know how to solve polynomials comfortably. Ultimately, it depends on exactly how the question is worded, what you have to do at this stage. Sometimes they might want you to show what the answers are in more detail because they might give you what one of the solutions is, so then you're expected to use algebra division to fully factorize it manually, etc., to reach your answers. If they don't say that in Maths A-level, further Maths A-level I should say, you're able to use a calculator to just solve the cubic for you using modern technology. Oh, amazing. Therefore, either way, you've got to solve that cubic. Obviously, if you're not given that information and you weren't given a calculator, if it's a university exam or whatever, you would end up having to just guess using factor theorem what one of the solutions is and then try to do algebra division, but that would be absolutely horrible, so nobody wants to do that. So I'm just going to use the calculator to solve this cubic for me, and if you do that, you will just get the three eigenvalues of 1, 2, and 5. Hooray! We found the eigenvalues. But how are we going to calculate the eigenvectors? Well, as we already mentioned, you just have to take your original matrix again, multiply it by the currently unknown 3D vector xyz and set that equal to one of your eigenvalues times by that mystery vector. And then you've got to find what vector satisfies that vector equation. Now, I have carefully crafted this example so that each of the eigenvalues is doing a slightly different thing when it comes to calculating the eigenvectors. So you'll get to see 3 different scenarios. So do stay around for them all because, as I said, there's some slightly different things I need to talk about for each one. I've decided to start with the eigenvalue of 2 because in this case it will lead to a scenario that's very similar to the one you'll get whenever you have a matrix that has any zeros in the elements that aren't in the leading diagonal. So therefore, let's go ahead and start calculating it. So multiplying out the stuff on the left hand side, you'll get some equations. So we'll get 3x plus y plus 2z is equal to 2x. We'll get minus x plus 2y minus z is equal to 2y, and then we'll get 2x minus y plus 3z is equal to 2z. Of course, those equations can be simplified, so if we simplify them, we will get x plus y plus 2z equals 0. We will get minus x minus z equals 0. And then we'll get 2x minus y plus z equals 0. Now, something you'll notice straight away is that these 3 equations aren't the same as each other, which is weird, because with the 2D ones, they often did. Not always, and that is why for the 2D ones, I did encourage people to still write all of the equations out for the rare chances when they do. But something worth noting with the 3D ones is this situation of the equations ending up being different from each other is far more common, and that's why you can't be lazy and just work out one of them and then use that one equation to work out the eigenvector. So that's something to bear in mind. Now, luckily, if you are doing this with any matrix that's got zeros in any of the elements except for the ones in the main diagonal, then you'll end up with a situation that by luck, well, not by luck because I designed this example to do this, but you'll end up with a situation like we have for this second equation, where one of your equations will only have 2 out of the 3 variables involved. What that allows you to do is a very similar approach to what we did for the 2D eigenvectors, where you do get to choose any value for one of the variables, and then this equation with only 2 of the variables involved can then help you work out what that second variable has got to be based on what your first variable choice was. So I could, for instance, choose that x is equal to 1, and then I could use the fact that if minus x minus z is equal to 0, that's telling me that z is equal to minus x. So therefore I know the value of z must be equal to minus 1 if x is equal to 1. Cool. We can then also work out the value of the third variable, because now that we've got the values of 2 of the variables, we just have to plug those into one of the other equations, one of the ones with 3 variables in, to then work out the value of that third variable. So if I now plug in x equals 1 and z equals minus 1 into there, then we will get this. So that tells me that y is equal to 1, and therefore we have found our first eigenvector. For the eigenvalue of lambda equals 2, we end up with the eigenvector of 1, 1, minus 1. Now it's worth pointing out this isn't the only eigenvector for this eigenvalue, but you just need to find one that works with this particular eigenvector. And we could find different ones by choosing a different value of x at the beginning, and then the values of y and z will adapt to that. Another thing to bear in mind is I only use the top 2 equations. Technically, your eigenvector should satisfy the third equation as well. And so what I often like to do is then once I've found my eigenvector, double check that it does satisfy that third equation as well, because if it doesn't, something's gone wrong. So therefore, we need to go ahead and do that. So we have 2, lots of 1, we have minus 1, and then we have plus minus 1. And in fact, that does come to 0, so therefore that's why I know this is a correct eigenvector for this matrix. Cool, so that's one of the eigenvectors now found. I am going to continue on and find the others though, because, as I said, this was a very particular scenario that we utilized to our advantage to help us find this first eigenvector, but it won't always happen necessarily. So I want to show you the other sort of scenarios that can happen and how you can deal with those as well. So we're now going to find the eigenvector of this matrix that is associated with the eigenvalue of, let's say, we'll do the one that's associated with 1. Let's do that one next. So luckily it's just going to be one lot of x, y, z, which is quite easy to do. So again, writing out all the equations, and to save you time, I'll speed up this bit of the video so you don't have to watch me writing it all out very slowly. Okay, so we've got our 3 equations, and once again you'll notice that this time all 3 are still different, but annoyingly this time we don't have any of the 3 equations only having 2 variables in. Now you can approach it like we did before, where you choose the value for one of the variables, but what you'd have to end up doing in this scenario if you wanted to go down that approach is you'd end up having to plug that into at least 2 of the equations, and then solve the simultaneous equations that will be created with the final 2 variables. And although you can do that, I don't know, some of you might find that a bit of a chore. It's up to you. It's interesting that I'm mentioning that term simultaneous equations though, because this stuff is actually ultimately starting to link back to that systems of equations chapter before, where we were looking at consistent, inconsistent, unique, infinite, no solutions, all that sort of stuff. And therefore, some of you might be looking at this going, well, can I save time by just using an inverse matrix, a 3x3 inverse on the calculator, to solve these 3 simultaneous equations to find what the eigenvector is? Unfortunately not, because the way these equations are always going to be set up, because with eigenvectors there's more than one eigenvector that technically goes with each eigenvalue, because you can have parallel vectors to your eigenvector that you chose that would still technically work. Therefore, there are technically infinite solutions to these systems of equations, and therefore the inverse matrix system won't work. However, there is another way you could go about finding the eigenvector if you don't want to do the whole plug a value of x, y, or z into these equations and solve the simultaneous equations you create with the final 2 variables. Instead, you just have to realize that what we've got here are planes. If we've got infinite solutions, which we do, then you know the planes are intersecting in a sheaf, which means basically there's a line of intersection, hence why there's infinite solutions. But therefore, what you have to do is find the direction vector for that line of intersection, because that is the eigenvector. And one way of finding the direction vector as the line of intersection between 2 planes is just to use the cross product. So all you've got to do is do the cross product of the 2 normal vectors for 2 of the planes. It could be any 2 out of the 3 planes, because it should come to the same no matter what. But again, you can also use the 3rd equation to then check your answer. So therefore, I'm just going to use the calculator, because calculators can do cross product, of course. I'm going to do 2, 1, 2, which is of course the normal vector of that first plane, cross product with the vector of the normal for that second plane, which is -1, 1, -1. If you work that out, that will come to -3, 0, 3. If you need a reminder about calculating cross product and also all this systems of equation stuff that I'm referencing here, then I do also have links to all that stuff in the description of this video as well. But anyway, therefore we've actually already found an eigenvector. You could check it works in the 3rd equation, so just to do that very quickly, 2 lots of -3 minus 0 plus 2 lots of 3 is indeed 0. Hooray! So therefore, for lambda equals 1, the eigenvector is -3, 0, 3. However, you could choose a vector that's parallel to that, so you could choose -1, 0, 1. That would be a bit more simple. But there you go, we're done with the second eigenvector. Let's work out a 3rd eigenvector, and this is the one that goes with the eigenvalue of 5. Again, I'm going to speed up the footage so that you don't have to watch me very slowly writing out all the algebra for the equations. So I'll join you in a few moments when all of those equations have been written out. And there you go, once again we've got our equations. The reason I wanted to go through this third case very quickly is although we still haven't got the situation where all three equations are the same as each other like we quite regularly have with the 2D ones, you will sometimes get a situation like this one where two of the three equations are the same as each other, which is something, I guess at least. Technically these two equations aren't currently the same as each other, but of course they are the same equation secretly because one is just -1 lots of the other equation. In reality though, this is just a visual difference to the other example. We're still going to calculate the answer doing the same thing as we did before. You're going to do or at least I'm going to do the cross product of -2, 1, 2, the normal vector of the first plane. Obviously, if you use the normal vector from the third plane as well, that's going to cause problems because the first and the third planes are parallel to each other, which leads to an unhelpful result with the cross product. So using the normal vector from the second plane instead, which is -1, -3, -1. That will come to an answer of 5, -4, 7. And there you go, we've got our third eigenvector that goes with our third eigenvalue. Again, you can check that your answer works, but we don't even need to do that this time because the fact the third equation is already identical to the first one, so you already know it should work. So there you go, we've found the eigenvalues and eigenvectors for a 3x3 matrix. However, there is one final thing we need to cover, and that is what to do if you get repeated eigenvalues for a 3x3 matrix. Well, let's take a look at an example. Once again, to find the eigenvalues, we just start by taking away lambda from all the elements in the main diagonal and keeping all the other elements exactly the same. And then we end up calculating the determinant and setting it equal to 0. And whatever values of lambda satisfy that will be our eigenvalues. Again, to save you time, I'm going to speed up this portion of the video so that you don't have to go through all the pain I am right now of having to manually multiply all these brackets, so we can skip straight ahead to just looking at the equation we get. Oh, well, I'm certainly regretting my life decisions after writing all that out, but we've now got the equation, and we can therefore now use a calculator to solve it. And if you do that, you would get the eigenvalues of -49, and then interestingly, the repeated eigenvalue of 49, repeated twice, obviously. Now, what impact does this have on finding eigenvectors? Because last time we dealt with repeated eigenvalues, we came across two different situations. Sometimes you would only get one eigenvector from the repeated eigenvalue. Despite it being repeated multiple times, there was only one eigenvector you could get from it because it's only one distinct value. But then other times you could technically find out that there was infinite choices to make, and therefore you just had to choose enough eigenvectors to make sure we had enough to match the number of dimensions we're dealing with overall. So let's take a look. First of all, obviously pointing out that if you're trying to find the eigenvector for the eigenvalue that's not repeated, it's not really any different from what you've already seen. So as lambda equals -49 is not repeated, just proceed as normal, and I'm not going to show all the working for that just because it's just in line with the other question we did. But therefore instead let's focus on that repeated eigenvalue of 49 because that's where the interesting stuff is happening. And once again, I'm going to speed up this part of the video so that you don't have to see me just spending ages writing all the algebra, and we can instead focus on the interesting bit, which is what the equations look like once we've discovered them. Okay, we've got our equations, and at first glance it looks like we've just ended up with the same usual situation we already have, but actually no. If you look really carefully, you'll realize that all three of these equations are actually the same equation. They're all boiling down to just getting us 2x plus 3y plus 6z equals 0. And so we have now got the situation we usually got with the 2D eigenvalues and eigenvectors, where although there's the multiple different equations we obtained while trying to find the eigenvectors, they're all the same as each other, so you only technically need to look at one of them. Interestingly, this means we have infinite solutions, and I'm not talking about infinite solutions like we had before where it was just infinite parallel vectors. We have infinite solutions that are going in infinite directions. Therefore, although there are infinite solutions, as we just need as many eigenvectors as there are dimensions, we need a total of 3 eigenvectors overall. One of those eigenvectors would be given by the other eigenvalue we had that wasn't repeated. So for this eigenvalue that was repeated twice, 49, we need 2 eigenvectors. So we just need to pick 2 non-parallel vectors, in other words 2 linearly independent vectors, to therefore end up with as many eigenvectors as we need. For those 2 eigenvectors, you are therefore allowed to pick any values of x, y, and z that satisfy this one equation that we've got. And to make our life easier when doing that, a lot of people will make one of the variables 0, and then another common choice that some people like to do is they make one of the variables 1 and then work out what the third variable must be to balance that all out. Unfortunately though, that will sometimes lead to more horrible numbers. So for instance, in this case, y would have to be minus 2/3 if x is 1 and z is equal to 0, which isn't particularly nice. So actually I'm not going to do that. Even though that would work, it would be a completely legitimate answer, so I'm just crossing it out for no real reason, to be honest. But therefore instead I'm going to make z equals 0. I'm going to instead choose x to be 3, because then it means y has to only be minus 2 to make it balance out, and they're all nicely integers instead. Basically, in reality, that is an eigenvector I could have got from the solution I had over there, but instead you've got a parallel vector version of that instead. And then we could instead choose to make a different variable 0 and then see how that affects things. So instead, this time I'm going to make x equals 0, and I'm going to therefore work out what y and z must be to react to that. Again, I could choose a value of y. You shouldn't pick y equals 0, because if 2 of them are 0, all 3 of them need to be 0, and 0, 0, 0 is a stupid vector. But therefore, I could pick y to be 2, for instance, because that means z only has to be minus 1 to therefore balance it out. So therefore 2 eigenvectors to go with the eigenvalue of 49 would be 3, minus 2, 0, and 0, 2, minus 1. They are linearly independent because neither of them are parallel to the other. Okay, that will do us for today's video. I hope you found this video interesting. It's a lot of algebra admittedly, so maybe carrying out these questions yourself isn't always the most interesting thing to do in the world unless there's a lot of zeros to speed the process up. But eigenvalues and eigenvectors in 3x3 matrices, done. Goodbye.